Hello, geometers. This is a recording for Platonic Esoteric Geometry Session 3 opening talk for the Platonic Academy of Melbourne. So people asked for the slides, so I thought what I would do is just maybe talk through the slides because they've got a bit of animation, and then I thought, well, I might as well just do the whole talk again and put it up on the web so people can go through that. So this is that introductory talk that we did in session 3. Remember in session 2, we had a look at the doubling of the square problem and saw how that related to Pythagoras' theorem. We'll go back to that a bit again and then look at how that that can be the basis for what we call a geometric expansion. So, and that was the exercise that we did in the second half of the session on in the third session. So there you go. Now you might remember that I started off the talk talking about the question of what is mysticism. You know, we have it on our website, Platonic Academy of Melbourne, Mysticism and Science. But what do we mean by mysticism? Well, the meaning that we use here is just fairly simple, really. It's that what is important in the philosophy, in a mystical philosophy, is insensible. So it's unseen, but it's also untouchable. It's outside all of the senses. So in Platonism, as we've seen in our introductory course and as we repeat all the time, Plato's forms are beyond the senses. And Plato's forms are the essence of the being of sensible things. So they're the essence of our experience, our sensual and perceptual experience. So he starts with the problem of, well, in a lot of the early dialogues, especially the social problems and problems of the good life, and that is that such things with what is justice, what is beauty, the form of beauty, the form of justice, the form of goodness. So these concepts that quite clearly we can see don't have as concepts. They can be expressed, there can be a just society or a just person, but as concepts in themselves, they are beyond the senses. But more than this, insensible forms are the being behind all of our experience. Right? Now, how do we imagine this? It's a rather extreme view, and it's important to see that it's a rather extreme view, because the normal situation is this: when you come to inquire about what is being and what is knowledge, is you start with objects of the senses, and you say, well, you know, this is surely something that I know exists. You know, I can feel it and touch it. It's here in my hand. Let's start with considering its existence in itself, and consider how I know its existence. So hence the exercise we did in the introductory course with the cup, where we inquire about how I know that the cup exists. And then we realize that we come to a problem, because everything I know about the cup in my experience is in my senses, which is in me. So what do I know of the cup that's not in me? Well, if everything is in my senses, in my sight, in my touch and everything, how do I know of its existence independent from me, as external to me? Well, I don't. And so there's a bit of a problem there, because it seems to have an independent existence, and yet I don't even know that it exists in itself. I only know it in my experience. So that's one approach, but it's not Plato's approach. Plato's approach would say, well, actually the essence of things is like the essence of number. So, and we've considered, well, okay, consider number 2. So we've got 2 cups, right? But where is 2 itself? I can always point to 2 things. I can use the numeral 2 to give us an understanding of you know, to point to symbolize 2 in itself. But what is 2 in itself? Like, is it in the objects, in the particular objects, in all the objects that have this together make 2, or is it in my head? Is it in the observed object, or is it in my head? What if the observer disappears? What if the objects disappear? What if, imagine a situation where there are no 2 things, would there still be 2? And this is the sort of thing you need to go away with and consider, to meditate on in a quiet place, because the discovery here is an internal discovery within you that can't be taught. Okay, it's something that you become aware of. It's this turning around the mind's eye and paying attention to the formal nature of things. The mistake is to see the forms as just other things. Whereas if we consider, for example, 2, the essence of number, consider the essence of the number 2, or any numbers, or numbers in general. And then we consider, well, what is their being actually? Do the meditation. The idea is that that will bring you to pay attention to the formal background, if you like, to our sensible experience. Okay, so considering numbers is one way. Another way is to consider geometry. So geometric figures. Now, remember, the whole reason we're doing geometry is because they did it in the academy, and because it was important, and because in the Republic, Plato says, well, more than anything else, perhaps, geometry is a gateway to the forms. So in geometry, we engage in sensible experience. We draw the diagrams and everything. And we create these sensible forms, these sensible objects, even if they're just diagrams, 2-dimensional. But then when we're dealing with them, we're considering their geometric form. So when we're talking about their symmetry, their asymmetry, their similarities, their differences, of the square, of the sphere, self-similarity, similarity to other spheres beyond scale, right? Remember when we did that? We're considering the way geometric figures, geometric shapes or whatever, the particularity of them express their invisible, insensible formal nature. And again, this is a meditation, this is an insight. This is an active insight, an activity that you need to do within yourself in order to become aware of what Plato is trying to get you to become aware of, which is the formal essence of things. So you start with number, you start with geometry as a gateway into seeing the formal mystical essence of things behind their sensible expression. Now, what I want to do is, like, mysticism is often a bit of a dirty word, and it sort of means, well, superstition or something like that. So what we want to do is get away from that. It might be related to superstition and ghosts and unseen forces and all that. They are unseen forces. Now, what I want to consider, though, is the ordinary way in which our mathematical thinking the mathematical thinking that we do every day. I'm not thinking necessarily of advanced mathematics. The mathematical thinking is mystical. So the ordinary way that geometry is mystical is not just this relationship between a particular square and the ideal square, or a particular sphere and the ideal sphere, and that ideal sphere relates all spheres and the ideal square relates all squares. So that's a way in which it's mystical. But there's also other ways in which geometry is mystical, and they're very ordinary ways. They're part of the ordinary thinking and teaching of geometry. So consider the surface of a solid object. The surface is not the thing. It's the limit. It's the distinction between the thing and its negation. Okay? So if we consider the sphere, the surface is not the sphere, nor is it the air around the sphere. It's where they meet. Okay? So we don't think of it as the top layer of molecules, because the top layer of molecules, the skin or whatever you like, is also something three-dimensional. Surface only has no depth. Okay? Now consider when I touch the sphere. This might be easier. Where is the surface of the sphere? Is it my skin? Is my skin the surface? No. Is the surface the foam? Well, no, it's not the foam. It's the distinction between the two. The sphere as a solid is visible. My finger is visible, but the surface, which distinguishes the two, is in itself invisible. This is the very ordinary mysticism of solid geometry. So we have this mystical surface with its limit, with its limit, which is the limit of the solid. And to consider a limit on the surface. Now, on the sphere, so we're talking about the surface now. On the surface, on this sphere, there is no limit, right? You can go in any direction, around and round. If you're a two-dimensional object, as Riemann would say in the Riemann sphere, you could go round and round and round and round and never stop. There's no limit, right? But now consider a flat surface like the surface of a page. Now remember, a page is three-dimensional, okay? You get out the microscope, it actually has a thickness. This is thicker paper than other paper. It has length, width, and depth, but we're imagining the surface of the paper because this is helpful, okay? Now what's the limit of the surface of the paper? Okay, the limit of a surface is a line. Okay, it's that line. So the line has length, but does the line have any width? So we draw a line on the page and we give it some width so we can see it. But in geometry, the line has no width. And we can again think of it as you've got the surface, and the limit of the surface is the line. The line has no width, just like the surface has no depth. All right. It's one-dimensional. It is like a cut or a chromatic difference. So a chromatic difference, we've done that before. We actually have color on the surface, and so we've got inside and we've got outside. Okay, inside, which is black, and outside, which is white. Right, we could draw a circle, but that has a width, and so that confuses us because we'd have inside, outside, and we could place our compass on the line. This is a better image of a pure limit or distinction. Okay, and with our paper surface, you can think of a limit as a cut. Okay, and so this is often expressed by Plato in modern discussions of limit. So I can make my square by making a cut in the page. And so the edges of the square are the distinction between the paper and not the paper. Okay. So consider a line as a limit. Now, remember when we were talking last week about whether the line is made up of points? Okay. So what is, well, we should first say, well, what is the limit of the line? The limit of the line are points. So in Euclid's geometry, one of the definitions of a line is the shortest distance between 2 points. But are the points at the limit part of the line? No, they're not. Because if they were, then the line would have, the point would have length. And the point has no length, no dimensionality at all. So it's triply mystical in a way, because it's the limit of a line, which itself is insensible, right? And the line is the limit of the surface, which itself is insensible. It's only when you get into the third dimension that you get our sensible reality. And remember, the Pythagoreans had this idea that when the point moves, think of the point as the tip of your pencil, when the point moves in time, generates a line. When the line moves, it generates the plane. And when the plane moves, it generates a solid. And only at that last move into the solid do we get our visible world, our sensible world. Our sensible world of experience is three-dimensional. Okay, so and remember last time we were considering, well, this line, what's it made up of? Is it made up of tiny points? Or can it be made up of tiny points? It can be made up of very small points. But can it be made up of tiny points? Well, it can't be made up of, it can be, can be made up of tiny dots, right, with very small widths, but it can't be made up of points, because points have no, I should say, length, have no, so if you add a point to a point, it's like adding 0 to 0. So there is this idea, this way of thinking, that actually the line is made up of infinitesimal points. As Berkeley would say, the ghosts of departed quantities. And this came up, remember, when we were discussing the infinitesimal calculus. Okay, but as Leibniz said, the infinitesimals are pointing to the line, but they're not actually the line. So that's two different ways of thinking about the line. The line is a continuum, or the line is made up of infinitesimal points, and as you move along it, you go from one point to the next. All right. So the point itself is triply mystical, but it's considered to be, by the Pythagoreans and the Platonists, to be the source of all the dimensions. All right, so that's pretty much that in introduction to Platonic mysticism. So don't be afraid of the term, because it's really what it's all about, and it's not something particularly alien to us. It's just, I guess, we don't pay attention to it. And Plato's saying, pay attention to the unseen insensible forms. All right. Okay, so what we're going to do now is we're going to move to show those slides about the square root of 2, the diagonal of the square. So I'll just put that slideshow up now. Okay, so hopefully you're seeing that screen. Okay, so let's have a look at this. So remember we started with the square and we thought, so well, how can we double the square? And we tried to do that on the graph paper, and so how long can we make the two sides equal sides so that we get double the area? And that was difficult to do because it wasn't a particular number of smaller squares, as we found out. And actually the length of the sides cannot be expressed as a definite number, as a definite ratio. So the way to do it is to draw a diagonal on the square and then to draw a square on that diagonal. And we found out that we could actually work out that it is double just by counting our triangles there, realizing that the two triangles in the original square are the same as each other, and they're also the same as the triangles in the second square. So think about that, have a look at that, work out why that's the case, and then it's just simply a matter of counting the triangles in the first square, which is 2, and then the triangles in the second square, which is 4. So it looks like we have doubled the square. Okay. Now, if we consider the first side as 1, so it's the unit square, we usually start in geometry, in this geometry with calling our first line 1. Doesn't matter how long it is in terms of centimeters or whatever you draw, you call that 1, and everything's in proportion to that. Now, we'll call the area there 1 because 1 times 1 equals 1. So the area of the square of sides 1 and 1 is 1. Okay, so that's an area of 1, and the other square has an area of 2. Okay, but what's the length of the side? So let's first have a look at how this also works for the squares on the sides being equal to the square on the diagonal. So, and that's a form of Pythagoras' theorem where you've got where you say the squares on the sides of the rectangle, in this case a square, equals the square on the diagonal, or the square on the hypotenuse if you're talking about a right angled triangle. So we can again count that the square on the sides are 1, have an area of 1, and the square on the diagonal has an area of 2. So the square on the sides added together equals the square on the diagonal. Some people learn this as a squared plus b squared equals c squared, where c squared is the square on the hypotenuse. All right, so let's move on. There we've got the doubling of the square and Pythagoras' theorem as expressed with the square. Of course, it can be generalized to all rectangles. Now, they use the expression of power and root. So the root of the area 1 is the square 1 is the square root of 1. So the area 1 is the power of the square root. Now, let's look at this square that has an area of 2. What is the square root of 2? Well, we can call it the square root of 2, but what is its length? Actually, it's irrational in the sense that it can't be expressed as a ratio. It can't. So when we write it in decimal numbers, it is 1.42, and the numbers just keep going on and on. We can't actually pin down what the square root of 2 is. And most diagonal numbers are like this: diagonals of squares or diagonals of rectangles, as we shall see. Okay, so we just continue to call it the square root of 2. The square root of 1, of course, is equals 1. The square root of 2 is we'll keep as square root of 2. Now, let's consider what the diagonal is on the new square. Okay, so have a look at where those question marks are and have a think about what the length of those lines are. So if you look down if you look at the top of the square, of course, it's going to have that length is going to have be the same as all the other lengths on the square. So it's going to be 1, and we can see think about it, how this is also 1. So the diagonal of the second square is precisely 1 plus 1, 2. Okay, so we're now looking at a little expansion on the doubling of the square. Let's have a look at this. So we've gone from the unit square with root 2. We've built the square on the side with sides that are the diagonal. So we've built a square on the diagonal which has length the diagonal, which is the square root of 2. Okay, now what about if we build a square on that diagonal? So we've repeated the process on the second square. The first square, we built a square on the diagonal, and on the second square, we've now built another square on its diagonal. Now, if we build a square on the diagonal, we double the square, right? No matter what we start with, what square we start with, it always doubles. Okay, and let's see how this works. So we worked out that the length of this diagonal is 2. So the square is a 2 by 2 square, and 2 by 2 gives an area of 4. So look at what we've got here. We've got the first square, and we built a square on the diagonal which doubles it. We've built another square on the diagonal of that square, and it's gone to 4. So see how we're getting the doubling series here. 1 is doubled to 2, 2 is doubled to 4. And imagine how we could continue with this. And I'll continue with it just a couple more times here on another diagram where we've gone from the square with an area of 1 to a square with an area of 2 to a square with an area of 4. And there's the diagonal there, which is length of 2 root 2. See root 2 here. So that must be root 2. So this is 2 root 2. And that has an area of 4. And the next one, sorry, the square on this diagonal has an area of 8. So we're going up the double series. 1, 2, 4, 8. And we can keep going. 1, double 1 is 2. Double 2 is 4. Double 4 is 8. Double 8 is 16. We're doubling every time. Okay. Now this is called a geometric progression. So the ratio between each number in the geometric progression is, in this case, double. In another case, it might be triple, or it might be half, or whatever it needs. It's just that it is the same ratio, or logos. Okay, so the logos here is double, and we get the double series, or the analogia of double. Okay, just to use the Platonic geometry terms, which will become important in the philosophy. Okay, so if we have a look now at my red circles down here, we're going from, in terms of the sides now, we're not looking at the area, we're now looking at the sides. So the first side of the square is 1, The side of the second square is root 2. The side of the third square is 2. Okay, and the side of the fourth square is 2 root 2. So we've got root 2 and then root 2 again here. So there's a series going, and then we've got, we then go up the next one, and we've got 4 1s, which makes 4. So we're getting another geometric series here, and this geometric series is increasing each time by the ratio of root 2. So we start with 1 times root 2 equals root 2. Root 2 times itself, remember, like the area of that second square is 2. 2 times root 2 is 2 root 2. 2 root 2 times root 2 makes 4. So what we do is we get the double series, but with these in-between terms. Okay, it's an analogia with the logos of root 2. Whereas the first one, the areas, is an analogia with the logos or ratio of double. Okay, or times 2, as we might say. Okay. So now I want to just show you how we can condense the first 3 steps into one simple diagram. And this will become important later when we look at squares and circles, but it is interesting in itself. So we've taken the first square down here and the second square, which is slightly obliterated there, and put the first and the second square inside the third square. So let's see how this works. So there's the first square there. Okay, it has an area of 1 and a side of 1. Now the square and the diagonal is easy to see. There's the diagonal and there's a new square. But look at this, look at its diagonal, and see how its diagonal length is the same as the length of the square which contains it. Okay, so that's the third square, because that's like the square, exactly identical to the square that would be drawn on its diagonal. So we get that third square. So the square with area of 4, square with area 2, and the square with area 1, all in the one diagram here. Okay. All right, so that's all we needed to show this week. We'll expand that a bit more next week. I'll just finish this little video here with what Nabil showed you last week about this basic principle in the drawings that we're going to be doing in the future regarding the bisecting of an angle. So if you have any 2 lines that cross, you've got the vertex where they cross, and we'll just take this example here of these 2 lines that we've got here, and we want to get the line exactly in the middle. So at any point here, we draw a line across there, it would be equal distance apart on each side. Okay, so we want to get exact middle line down these. How do we do that? Now we've already done it, but you probably didn't notice. Okay, so first of all, you draw a circle. Any circle can be any size, actually. Some sizes are more convenient than others, but you draw a circle with center around the vertex, and notice how it crosses the line, the 2 sides of the angle. And then you draw 2 more circles, and they can be an arbitrary length, but some are better than others. So long as they cross over, so long as those circles cross each other. See, they're crossing at 2 points here. So long as they cross, they'll do the job. So first of all, the circle at the vertex, and then where that circle, the purple circle here, crosses the 2 lines, draw 2 other circles. Find the cross of the 2 circles centered on the point equidistant from the vertex. So see how these points will be equidistant from the vertex. Okay, so we've drawn those 2 circles, and where they cross, that gives us the point through which our line goes. Now this will work no matter what angle you have your lines at. It will always, this same principle will always work. Draw the first circle and then draw those second two circles and then find the cross and then find the line, no matter what angle it is. Now that includes even where the angle's straightened out to be a straight line. Here I've got a straight line with a point at the center, and I've drawn the square in there to show that it's two right angles, just a symbol used in geometry, and we've drawn a circle around that. Okay, now what will be of that angle, what will be the bisection? What's the bisection of 180 degrees? 90 degrees. This is how we get our candle flame axis, or our vertical axis, or our north axis, as just the language we've been using. The vertical axis we find by bisecting the 180 degree or straight line angle. Okay, so we've drawn our first circle, and then we draw circles where those circles intersect the lines. And then we find their intersection, and then we get our vertical axis. So that's how we're finding the vertical axis all the time. Now, often what we'll do, and as we get more experience especially, we will just draw these little crosses approximately where we're expecting the line to be. Okay, but it's good to remember that these two lines are actually just parts of the bigger circle. And it's good to look at this and understand, to contemplate it on your own, and to understand why it always works. Because if you understand why it always works, then you're getting inside the geometry, you're getting to the formal nature that's being expressed in the geometry. And this is a good thing to do with every exercise, to understand in some sort of intuitive sort of way. You don't have to give an account of it. I could try to explain now why it always works. Play around with a few lines, and after a while you'll see why it always works. So this is the sort of thing we want to keep doing with our geometry. Okay, I'm going to end that slideshow. And that's pretty much it. I probably talked on a bit more than I did on the night, but I hope that that helps you to review what we've already done with the geometry, what the mysticism is, what we're pointing towards, and then what's actually going on with these squares and with the square expansions and with the bisecting of the lines. All of these meditations are interesting in themselves, but they're meditations that help you get towards turning the mind's eye around and paying attention to the insensible forms. Okay, I'll leave you with that, and we'll see you next week.